Hey guys, welcome back to the channel. If it's your first time here, my name is Aiden Potts and we go through math and physics tutorials as well as how to improve the mindset and learning skills of a student. In today's video, we'll be proving the double angle identities that are necessary to use when we're trying to solve and verify trigonometric identities. This is video number 2 in a multi-part series related to proving the trigonometric identities, and then we'll finish off by going through a lot of them together and going through a lot of example problems. By the end of this video, you'll be able to understand where the double angle identities come from and how to derive them from our previous derivations. Being able to derive the double angle identities from our previous derivations is much more powerful than just writing out the identities, dozens of times. Once you go through and derive it once or twice, you'll be able to do that every single time, and then you actually won't need to memorize them, thus saving you a lot of time. If you guys like this content, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. Okay, so for the double angle identities, we're actually going to use our previously derived compound angle identities. And what you'll find is the double angle identities actually are a lot easier to get once you have those compound angle identities. So some of the double angle identities are sine of 2x, cos of 2x, and tan of 2x. And you can see that cos of 2x can be expressed in 3 separate ways. But a lot of the time teachers will try and get you to memorize this, when in reality it's just this Pythagorean theorem identity right here that accounts for these other 2 derivations, or I guess ways of writing it. Okay, so we'll start with sine of 2x, and this identity equals 2 sine x cos x. We'll prove it using this compound angle identity. If you don't know where this comes from, I did a previous video in part 1 of this series where we go through all the compound angle identities. So we're going to start with this compound angle, this addition formula for sine, and I'm going to say that b, I'll do it in red, I'll say that b is equal to a. So angle b is equal to a. So I'm still going to write sine of the same exact thing, but wherever I see a b, I'm just going to place an a. So plus, instead of b, it's going to be a equals sine a, and then cos, not of b, but of a now, plus sine a cos a. Now, this can be rewritten as sine of 2a is equal to, well, this and this are the exact same thing. So we can just write, it's like saying x plus x will equal 2x. We can just say 2 sine a cos a is equal to these 2 expressions. And right there we get the double angle identity for sine. This is the identity number 1. Okay, so for cos of 2x, or cos of the double angle identity for cos, we're going to try and get to this, I guess, result here. And we're going to start again with the compound angle identity for cos of a plus b, so the addition formula. So again, I'm just going to say b is equal to a. Wherever I see a b, I will just replace it with an a. So I'll have cos of a minus sine of a, sine of a. And now I can rewrite this as cos of 2a is equal to, well, this will just be cos squared a, and this will be minus sine squared a. So just like that, we have our another identity here, which is number 2, or I guess it's the first identity for cos of 2a. And again, it's not all that hard. We just start from the compound angle formula and just add in a plus a instead of a plus b. But you'll notice that cos of 2x can actually be written in a couple different ways. And the way I'll do that and show you kind of how it's written, we have to come back to the unit circle. So I have to use our unit circle definition. And so this purple line, I can make a right angle. And again, a unit circle is a circle that has a radius 1 and it's centered around the origin. So this purple line, I can say, if I've created this as a right triangle, is the opposite side. And then I'll do it in blue. This horizontal distance here, this is really just the adjacent side of this triangle. So now I can say that sine of theta is equal to, well, it's the opposite side over the hypotenuse. But in this case, the hypotenuse is just 1. So we end up actually getting sine theta is equal to the opposite side. If that's confusing, I have another video that I'll link in the cards that goes through the unit circle derivation a little bit more clearly. Now I'm going to look at cos theta. So cos of theta is equal to adjacent over hypotenuse. Again, the hypotenuse is just 1 because it's this unit circle. So cos of theta will equal the adjacent side. So now I have this triangle where I have 1 is the hypotenuse, and then the opposite side, that's going to be sine of theta, and the adjacent side, well, that will be cos of theta. So these sine of theta and cos of theta, they actually represent the length of this triangle. And we know that from Pythagorean theorem, a squared plus b squared equals c squared, where c is the hypotenuse of the triangle. now that we have a squared, let's just say a is equal to cos, so we'll have cos squared theta plus sine squared theta is equal to 1. Again, because 1 squared, which is our c in this case, is just 1, 1 squared is 1. So now this is the Pythagorean theorem identity, and this is super important. Whenever you see a 1 for these trigonometric problems or trigonometric identities that are going to come up, using this theorem here, whenever you see a 1 and placing all this, will actually be very helpful. But now I want to show you how to get the remaining double angle identities for cos, and it's really just using this Pythagorean theorem identity. So I'm going to rewrite this Pythagorean theorem identity as cos squared theta minus, or is equal to 1 minus sine squared theta. So I just brought that sine squared over to the side with the 1 on it. And then now, wherever I see a cos squared theta in this equation, I'm just going to replace it with this part of the equation. So we'll end up getting cos of 2a is equal to, well, now we have a cos squared of a, so that's going to be 1 minus sine squared a, and then it'll be minus sine squared a. And here I'm using a's, and then for the identity I use thetas, but it's just a variable, it's just representing an angle. So now if I collect like terms, I'll end up getting cos of 2a is 1 minus 2 sine squared a, and that is our third trigonometric or double angle identity. Now to get our fourth and our final double angle identity for cos, what I'm going to do is instead of solving for cos squared theta using this Pythagorean theorem identity, I'm going to solve for sine squared theta. So now it'll be 1 minus cos squared theta, and I'm going to do the exact same process. Wherever I see a sine squared theta in this formula, I'm just going to replace it with this 1 minus cos squared theta. So what I'll end up getting will be cos of 2a is equal to cos squared of a minus 1 minus cos squared of a. And once I distribute this negative sign and collect like terms, I'll get cos of 2a is really equal to cos, or 2 cos squared a minus 1. And this would represent our fourth double angle identity and our final double angle identity for cos. So now moving on to the double angle identity for tan. So again, we're going to go back to our compound angle identity for tan, which is tan a plus b. This is tan a plus tan b over 1 minus tan a tan b. Again, I go through a derivation of this in the previous video, so if you don't know what this means or don't know where this comes from, you can check out that video there. So now I'm just going to say b is equal to a. Wherever I see a b, I'll replace it with an a. So this will be a plus a is equal to tan of a plus tan of a over 1 minus tan of a tan of a. And if I simplify this, I'll get tan of 2a is equal to 2 tan a over 1 minus tan squared of a. And this is our sixth and final double angle identity. So I just wanted to make this quick video on the double angle identities. There's not all that much to it, but again, it's really important that you go through the derivations and the concepts yourselves because it'll ingrain in your memory a lot better. I really am against kind of memorizing these identities because when you have all these equations and you finally have them on like a formula sheet and you start looking at them before you start the problem, you'll kind of get this thing called like, paralysis by analysis where you don't know where to start and you just kind of get overwhelmed. But if you know where they all come from, it's a lot easier to see the relationships before you even start the problem. If you guys got some value out of this video, I'd really appreciate you liking this video and subscribing to the channel to see more videos just like this. If you have any topics or subjects you want me to cover, let me know down in the comments below and I'll put them in the next video. Thanks again, and I'll see you guys in the next video.